Yes guys, today we're proving why the derivative of x to the n equals n times x to the n minus 1. So let's take any part of the graph x to the n. Now x to the n can look like a lot of things. So let's just take a section of it. So let's just say x to the n looks like that, for example. Now let's take the point x and the point, let me just draw it actually, x plus h. Now, and we're sketching fx. Now this point here would be f of x, and this point here would be f of x plus h. Now f of x plus h equals x plus h to the n, and f of x just equals x to the n. And we know when we got the derivative, so dy over dx, or in this case f dash x, we're looking at the gradient. So the gradient between the points x and x plus h is, gradient, f of dash x equals change in y over change in x. So f of x plus h minus f of x over change in y, so x plus h minus x. And we said f of x plus h was x plus h to the n, and f of x was x to the n, and x plus h minus x, just h. So this would be the gradient of the straight line going through these 2 points. Sorry, this bit here is wrong. This is not, this is just the gradient of a line. Let's draw a line on and call it line L. It's gradient of L. Now we want the gradient at just the point x, because we're over here f of x where x to the n is, and we want to know what the change, the change at this point is. So what we do is we take the limit as h goes to 0, so at this point goes here essentially, because x plus 0 is obviously just x, so this point just becomes here. So now f dash x, or we could say the derivative of x to the n equals the limit as h goes to 0, then x plus h to the n minus x to the n over h. Now there's a few ways we can evaluate this to get our derivative. So let's go through. So method 1 uses some factorization. So let's recall this identity, which is a to the n minus b to the n equals a minus b, a to the n minus 1 plus a to the n minus 2, drop the power, pass it over to b, plus up until a to the b n minus 2 plus b to the n minus 1. Alright, so we're going to be using this identity, so let's bring over this, copy, right. Right, we've got all that sorted. So we can see a to the n minus b to the n here, so a here and b here. So what we do, if we take the limit h goes to 0 and we use our identity on the numerator, so we have x plus h minus x, so that's a minus b multiplied by x plus h to the n minus 1 plus x plus h to the n minus 2 multiplied by b, which is x in our case. Let's drag this line. It's not right at the next few terms. Let's say up until b to the n minus 1, so that's x to the n minus 1. And then over h. Now, this part here just becomes h, which can cancel with the h on the bottom. So we can say the limit as h goes to 0, and we've just got the numerator without the first bracket. So we've got x plus h to the n minus 1 plus x plus h to the n minus 2x plus x to the n minus 1. Right. What next? Now we should take limits. So when each term becomes x to the n, so when each h goes towards 0, so this h here becomes non-existent, non-existent, and so on and so forth. So we'd have x to the n minus 1 plus x to the n minus 2x plus x to the n minus 1. Now, if we simplify this, x to the n minus 1 plus x to the n, well, x to the 1, basically the same, so just add the powers, plus x to the n minus 1. Now, how many times does this happen? Well, this x to the n minus 1 repeats itself, I believe, n times, so we can say we have n times x to the n minus 1. The reason we have this term repeating n times, well, if we go back up here, this bracket here, we had a, this is our first a, let's use our b, so we had b0, b1, b n minus 2, b n minus 1, so we had n times b terms, so then we can say that we have n times x to the n minus 1 terms, which shows that, yeah, that's proven. Derivative of x to the n is n times x to the n minus 1. That's it. So method 2 now, slightly more boring. So we said derivative of dx, which I know that x to the n was limit of n minus x to the n over h. So using the binomial expansion, we can expand x plus h to the n. So we have x to the n plus n choose 1, x to the n minus 1 times h plus n choose 2, x to the n minus 2 h2 plus last time will be h to the n, then we're minusing x to the n all over h. Now what we can do, we can cancel the x to the n's at the end, so that can just disappear. So we're left with the limit actually, we don't even need to write it out again. Let's just draw a red line through them. X to the n. How can we evaluate this further? Well, we can just cancel all the h's at the top with our denominator h. So we have n choose 1 x to the n minus 1 plus n choose 2 x to the n minus 2 h squared over h becomes h plus 2 h to the n minus 1. Now if you take the limits as h goes to 0, well, any term with a h will just disappear because h becomes 0. So we're left with, just put back around that, n choose 1 x to the n minus 1. The first term remains untouched because it doesn't contain a h. Second term disappears because of this h. And then every other term after that will have a h. So they will all disappear. And n choose 1 we know to be n. So n times x to the n minus 1. And that's our derivative of x to the n. And now you've got two ways of proving the derivative of x to the n. Nice.